We turn a tap counterclockwise, that is against the direction of the clock, it moves up, that is opening. And if we turn it clockwise, that is in the direction of the clock, it moves down, that is closing. Now, the rotation of the tap, that is the turning of the tap, is on a horizontal axis, on a horizontal plane, pardon, which will label x, y, while the translation, that is the upward downward movement, is along the vertical axis, which we will denote by z. Now, let us represent the forces turning the tap by vectors A and B. Okay, and the direction of translation of the system by unit vectors n and minus n in the downward vertical. Now, the angle between these two vectors, we call it theta. So now, turning the system counterclockwise is akin to turning A through the axis of B. So that is A across B, and that produces a movement in the upward Z axis, which we will define as A cross B, which is a cross product of A and B. A cross B. And if we turn it clockwise, then it moves downwards, that's in the negative vertical axis. We define that as B cross A, which is the same thing as A cross B in the negative axis, that is minus A cross B. Now, these vectors have components in the three axes. For example, A has a component, this, which we'll call let's call it A1, call this A2, and it will also have a component, this here, let's call this A3. And just as we represent the direction of translation of the system by unit vectors n and n, we can also represent the direction, the unit vectors in each of these axes by this one I, j in the y direction, and k in the z axis. Now, what the cross product now means is turning A across the path of B and turning B across the path of A. Now, if we slide B, if we translate B along the axis of A downwards, we'll have something like this. So B comes here, and we complete the diagram. We complete the diagram here, we will have a parallelogram. We have a parallelogram. Let's label it A, B, C, D. Now, from our knowledge of plane geometry, from our knowledge of mensuration, we know that the area of a parallelogram is the base AB times the height, which is let's label here E times the height DE. Now, from our knowledge of trigonometric ratios, if we apply trigonometric ratios to this diagram, sine of theta is equal to opposite, that is DE, is equal to DE all over the hypotenuse AD. Now DE is our height, and AD is the vector B. Okay, so this is the magnitude of B. Therefore, DE is equal to B sine theta. So the area is AB, which is the vector, the magnitude of vector A, times DE, which is the magnitude of the vector B sine theta. This is the cross product of A and B. Now, algebraically, like we did show here, A has components A1, A2, and A3 in the directions of X, Y, and Z respectively. So we can write A in terms of its components as A1, that's A in the direction of X, plus A2 J, that's in the direction of J, plus A3 K in the direction of K. Likewise, we can write B in component form as B1I plus B2J plus B3K. Hence, the cross product of A and B will give us A1I plus A2J plus A3K times B1I plus B2J plus B3K in these directions respectively. So on expansion, we get A1I times B1I, which gives us A1 B1 I cross I. Then A1I multiplying B2J gives us A1 B2 I cross J, plus A1I multiplying B3K gives us A1 B3 I cross K. Then we move to A2J. That gives us A2J times B1I, which is A2 B1 J cross I. Note that J cross I is not the same thing as I cross J. We are talking of two different directions entirely. Plus A2J times B2J will give us A2 B2 J cross J, plus A2J times multiplying B3K will give us A2 B3 J cross K. Then we move over to A3K. A3K times B1I will give us A3 B1 K cross I, plus A3K times B2J will give us A3 B2 K cross J, plus A3K times B3K will give us A3 B3 K cross K. Now, I cross I means turning I across its own axis, that's turning I across I, which is not possible. So we say I cross I is equal to 0. Same thing with J cross J and K cross K. Now, I cross J means we are turning I around J. As moving I across. Let's make this diagram simpler by cleaning all these things. Let's make this diagram simpler like this. Okay, and leave only the unit vectors in the X, Y, Z axis. So this is our Y axis. We have I, J, K here. Now, I cross J means we are turning I around the J, which we move the system upwards in the direction of K. That's I cross J will give us K. And if we turn J through I, then we are closing the tab. That give us a move minus K. J cross I is equal to minus K. And looking, that's from the left now. Now looking from the back, if we turn K in the direction of I, then we are closing the tab. That's in the direction of J. We are opening the tab backwards, so it will move backwards. That's K cross J will give us minus I. While if we turn J across K in the direction of K, the system will move in the positive direction of X. That means J cross K will give us I. Then which one is left? I cross K. Now looking from the back here, from the left, if we turn K in the direction of I, that's clockwise, that's K cross I, the system will close in the direction of Y. If we move forward in the direction of Y, that will give us J. And if we turn I in the direction of K, we are opening the system, so it will move backwards. That's in the negative direction of Y. So I cross K is equal to minus J. So let's substitute this in our equation. We have that right now, this one is already okay. We've established this, and that I cross J is equal to K. We have established this in the other page, in the other slide. So A cross B is equal to, this becomes 0. This becomes I cross J is equal to K. That will give us A1 B2 K plus I cross K is equal to I cross K is equal to minus J. So we will have A1 B3 minus J. Then J cross I gives us minus K plus A2 B1 minus K. Then J cross J gives us 0, so A2 B2 is out. Then A2 B3 J cross K will give us A2 B3 J cross K is I plus A3B1 K cross I is equal to J. That means A3B1 J. Then A3B2 K cross J gives us minus I plus A3B2 in the direction of in the negative x axis. Then K cross K is 0, so this one is also out of the system. So we now have A cross B is equal to A1B2K minus A1B3J minus A2B1K plus A2B3I plus A3B1J minus A3B2I. Now we can collect like terms. We will now have a terms in I. Let's deal with I first. We have A2B3I minus A3B2I. So A cross B give us A2B3I minus A3B2I. Then terms in J, we have A3B1J minus A1B3J plus A3B1J minus A1B3J. Then terms in K, we have A3B1. We have A terms in K, A2B1K minus A1B2K minus A2B1K. That is A1B2K minus A2B1K. Now we can write these vectors. Okay, firstly, let's factorize. We have A cross B gives us A2B3 minus A3B2I. Okay, we have a minus A1B3, that's A2B3 for J. Okay, that's A1B3 minus A3B1J. Now if we multiply this one out, we'll get a positive, so it's correct. Plus the last one, we have A1B2 minus A2B1K. So this is in the form of determinant of a matrix. We are familiar with it, so we can write this in matrix determinant form as A cross B is I J K. We have A1, A2, A3, B1, B2, B3. And you know that if we want to find the determinant of this matrix, we cover the row and column of this. We'll get I multiplied by A2, B3 minus A3, B2, I. Then minus J, we have A1, B3 minus A3, B1. Then plus K, we cover the row and column. We have A1, B2 minus A2, B1. So this is the vector product in determinant form, that's algebraic form, while the one we got earlier was the vector product in the geometric form. So this is the cross product of vectors.
If you like this video, please subscribe to my channel and turn on notifications for more videos like this. You may as well visit my website www.everydaymaths360.com for more lessons, learning materials, and prep packs comprising over 1,000 thoroughly explained solved practice problems. Thank you.